So in this video we're going to identify what the basis of a vector space is. So we define the basis of a vector space this way. If we have a set of linearly independent vectors that come from the vector space, and then if those vectors span the vector space, then we say that that set of linearly independent vectors is a basis for the vector space. And then the number of vectors, the number of linearly independent vectors that span the vector space, we identified that as the dimension of the vector space. So the important thing here is, in the previous videos we've identified what linearly independent is and how to determine whether vectors are linearly independent, and we've defined what it means to span and how to identify whether something spans or not. So given a vector space and a set of vectors, what we need to do to determine if we have a basis is we need to make sure that they're linearly independent and that they span the space. So for example, in R2, if we take the set of vectors 1, 0 and 0, 1, we could ask the question whether this set of two vectors is a spanning set, is a basis for the vector space R2. And to do that, we would need to make sure both of these criteria are met. So in the previous video, we actually already showed that this set of two vectors spans R2, and we did that by taking an arbitrary vector from R2, x1, x2, where x1, x2 are just real numbers. So this is what the arbitrary vector coming from R2 looks like, and we identified that every arbitrary vector in R2 could be written as a linear combination of the vectors 1, 0 and 0, 1 by doing exactly what I'm doing right now. So clearly when you distribute the x sub 1 and x sub 2 and add these together, you get this vector. So the vector space R2 is completely spanned by these two vectors. The other thing we would need to do is identify that they're linearly independent. So remember, when we test for linear independence, we take a scalar c sub 1 and we multiply it by the vector 1, 0, plus we take a scalar c sub 2 and we multiply it by the other vector 0, 1, and it was convenient to do this using column vectors, and we set this equal to the 0 vector. And remember, for linear independence, our vectors are linearly independent if the only solution to this equation is the trivial solution c sub 1 equals c sub 2 equals 0. If we can find any non-trivial solution, then there will be infinitely many non-trivial solutions, and we won't have a linearly independent set. And the reason for writing it in the column vector form is it immediately translates into an augmented matrix form. And in fact, you can see that the augmented matrix it translates into is already in reduced row echelon form. And this is the c sub 1 column and the c sub 2 column. So right away we can see that c sub 1 equals 0 and c sub 2 equals 0. So the only solutions are the trivial solutions. So this set of vectors 1, 0, 0, 1 spans the vector space R2 and is linearly independent in R2, because when we write it as a when we write the 0 vector as a linear combination of 1, 0 and 0, 1, only the trivial solution works. If we were working in R3 and we took the set of vectors 1, 0, 0, 0, 1, 0, 0, 0, 1, it is again easy to show that this set of vectors spans the vector space R3, because an arbitrary vector in R3 looks like this: x sub 1, x sub 2, x sub 3, and can be easily written as a linear combination. Let's move this down. X sub 1, x sub 2. Grab that arbitrary vector out of the vector space, and it's easy to show that this vector can be written as a linear combination of these three vectors this way: x sub 1 times 1, 0, 0, plus x sub 2 times 0, 1, 0, plus x sub 3 times 0, 0, 1. So clearly any arbitrary vector in R3 is a linear combination of the three vectors in this set. And these are going to be linearly independent vectors, because when we take scalar c sub 1 and multiply it by 1, 0, 0, plus scalar c sub 2 and multiply it by vector 0, 1, 0, plus c sub 3 and multiply it by vector 0, 0, 1, and set that equal to the 0 vector in R3, it is easy to see that the only solution to this system of three equations in three unknowns is the trivial solution. C sub 1 equals 0, C sub 2 equals 0, C sub 3 equals 0. Therefore, these three vectors are linearly independent in the vector space R3. And R3 is a three-dimensional vector space because it required three linearly independent vectors to span it, just like R2 is a two-dimensional vector space because it takes two linearly independent vectors to span it. The reason for using this example and this example is to introduce the notion of the standard basis for a vector space. So in R2, this set of vectors that we just looked at, we call it the standard basis for R2. The thing to note is that if we have an xy set of coordinate systems, that those vectors are unit vectors along the x and y axes. And in a three-dimensional coordinate system, these constitute unit vectors along the x, y, and z axes. And this is called the standard basis for R3. And in general, the standard basis for Rn is going to be take n minus 1 zeros and 1 number 1 and find all possible vector combinations that include n minus 1 zeros and 1, 1, and that forms your standard basis for Rn.